Okay, so last time we covered an exciting topic. We covered scattering, and we sort of began to see the seeds of quantum field theory. And the way we sort of started to see the seeds of quantum field theory was when we looked at scattering as a Born series, right? As a series of scattering amplitudes, right? Coming from a set of diagrams. So if you recall from last week, the big takeaway from last week was we have to calculate a scattering amplitude for any scattering process, right? Just like in quantum mechanics, we're dealing with probabilities, we compute probability amplitudes. Similarly, we compute scattering amplitudes. I won't go into all the specifics. That's what we did last week. And then we know that each process is going to contribute differently to the scattering amplitude, right? And each additional process is going to become more complicated. So you could have two interactions, right? And so on and so forth. And this is what we sort of figured out last time. And we derived the Born series. And we saw that each interaction happens via Green's function, and we did all of that sort of stuff. So that was last class. Now, basically, what we did last class was perturbation theory. Okay, what is perturbation theory in a nutshell? Perturbation theory is really important. I had mentioned when we studied the hydrogen atom that the hydrogen atom is one of the very few systems we can actually solve in quantum mechanics. It's actually one of the very few systems we can solve without making any approximations, like major approximations. Almost every other problem in quantum mechanics, we're going to need to use perturbation theory. Perturbation theory is an approximation method, right? So think about it this way. When I give you a function, cosine x, right? And I ask you guys, write out the Taylor series of cosine x. You guys should all know how to do that, hopefully. You write out the Taylor series for cosine x, you get an approximation, right? That approximation, what that allows you to do is it allows you to take the first few terms of the sequence, right? And then drop everything else, right? So in a sense, that's also a kind of perturbation theory. All perturbation theory is an approximation scheme. Why do I use the word perturbation? Because in most quantum mechanical systems, you're not going to have a clean potential. Okay, your potential is not going to be sort of easy and uniform and symmetric. You're going to have a potential that gets a little push, that gets a little kick, that gets a force acted on it, right? If you have an interaction between two particles, that's also like a sort of perturbation. Of course, we saw that these scatterings off the particle, which we can also call interactions at these vertices, were all represented by Green's functions, right? Which were like g of x1 minus x, or I even used, last time I used little g, which will become apparent when we go to QFT. But all of these things are a form of perturbation theory. In other words, these diagrams, this expansion really comes from perturbation series expansion. And when we do the path integral, you'll see this more explicitly. So the whole goal of today's class is to see what we can do if we have a system. For example, let's think about the infinite square well again. So we have some boundary A, we have the well, it's in some, the free particle is in some potential, right? It's bouncing around the walls. Now we want to consider what will happen if we perturb this square well. In other words, if we give the potential a little kick at some point, right? We give the potential some force. So now the particle's bouncing around, but it has this little divot to work with. What will we do in this situation? And the reality is, in nature, most situations, most physical circumstances are perturbed potentials. We always have to deal with perturbed potentials. And you'll see that more clearly when we look at different systems. So that's the goal for today. How do we get the dynamics of this? And we're going to have to use approximation schemes. Okay, let's begin. So the kind of perturbation theory we're going to be doing today is called time-independent perturbation theory. And actually today my plan is I'm going to show you the basics, and I'm actually going to do a sort of a flipped classroom today. I'm going to do some problems today, like really work out problems, work out calculations, so you can actually see how to calculate. Like we have to do a power series expansion today. I'm going to show you exactly how to do it. So all of you know how to do power series expansions. Okay, so we're going to go slow with calculations today. The flip side of that is you're going to have to do some reading on your own. So I figured I'd actually do some problems today. I'd really show you, because I feel like some of you guys still aren't comfortable with doing calculations on your own, which is fine. But at the cost of that, you're going to have to do some reading at home. So I'll tell you what to read about online or whatever. Okay, let's begin. So I start with my ground state Schrodinger equation. Okay, and now these n's and zeros are just labels. So the n could be any state of psi, first state, second state, any multiple state of psi. And the 0 tells me that I am in the ground state. Okay, so this is my basic Schrodinger equation. I'm writing it in sort of a suggestive format. Okay, and then we obviously have our orthonormal condition. When is this equal to 1? Can someone tell me really quick?
When those are equal.
Exactly. So when n equals m, this is equal to 1. Right, good. Okay, now we perturb our, let's say we perturb our potential. So now our Schrodinger equation becomes this. Right, all I do is get rid of the zeros. I'm moving to some higher state. Okay, that's all I do. That's all that 0 meant. I'm taking you from the ground state to some excited state. Okay, that's just a notational thing. And now let's look at this equation. Okay, right. So let's see what I can do to this thing. Okay, so we're going to approximate each one of these objects in a perturbation series: the Hamiltonian, the wave function, and the energy. Okay, so I'm going to write the Hamiltonian in this way: h equals h naught plus lambda h1. So lambda is some really small number. Okay, so it's some really small number. So this is why I can write this as some approximation. I can take the ground state Hamiltonian, split it up from the first excited state Hamiltonian, right? That piece that tells me about the first excited state, and multiply it by some really small number, which will give me a good approximation of the entire Hamiltonian. Similarly, in field theory, what we'll see is we'll have some function called a Lagrangian, and we'll split it up into a free Lagrangian and an interaction part of the Lagrangian. So we do this sort of thing all the time where we split it up. Okay, so this is my expression for the Hamiltonian in perturbation theory. Okay, and this is just some small scalar. It doesn't really matter what it is. Similarly, I'll write psi n as a power series in lambda. So this is just sine 0 plus lambda sine 1 plus lambda squared sine 2. Okay, and we're going higher order as well. So as we get higher in the energy, we get higher order terms in lambda. Okay, similarly, I'm going to do the same thing for the energy. En equals En0 plus lambda En1 plus lambda squared En2. Is this all okay? This is just me expanding it out in a series and approximating each object in my Schrodinger equation. Nothing crazy. So now let me plug this into star and get a perturbed approximate Schrodinger equation. So I have h naught plus lambda h1, and I have psi n, so psi n 0 plus lambda sine 1 plus lambda squared sine 2 equals En, which again is my perturbed energy or power series energy, whatever you want to call it. Lambda En1 plus lambda squared En2 times psi n again. So it's just psi n 0 lambda sine 1 plus lambda squared sine 2. Okay, so now I have my Schrodinger equation. I've approximated each term in a power series, and I have some approximate equation. Now I'm going to do some algebra to this. I'm going to group my terms corresponding to their powers in lambda. So what I want is I want a series of coupled equations, right? I want my Schrodinger equation to lowest order. I want my Schrodinger equation to first order. And I want my Schrodinger equation to second order in lambda. So this is really easy to do because I've already written it out in the power series. Now I can just group terms accordingly. So let's do that. Let's group terms accordingly. So I'm going to group the lowest order terms first. H0 sine 0 plus lambda. Now I'll group my terms according to lambda. H1, I'll write this here so it's easier to see. So these are my lambda terms. H1 sine 0 plus H0 sine 1 plus lambda squared. And we'll group the lambda squared terms. And I'm looking at the left-hand side here right now, right? So I have H0 sine squared plus H1 sine 1. Okay, so I've just grouped them according to powers of lambda. And I'm going to do the same thing on the right-hand side. Nothing crazy. En 0 sine 0 plus lambda. Let me see what I can group here. I have En1 sine 0 plus En0 sine 1 plus lambda squared. And I think I'm going to, I think I'm going to get three terms here. So I'm going to get an En, I shouldn't say squared, I should say 2. That's not a power. That's just a second excitation. So forgive me for saying squared. En2 sine 0 plus sine 2 En0 plus, what else can I do here? I have sine 1 En1. Yeah, I think that's it. Plus sine 1 En1. Okay, so I've done my grouping. And now I've received 3 equations, right, which are coupled. By coupled, I mean I can kind of remove them and work with them individually. Anyone have any questions so far? I'm just checking if I did that right. Yep, looks good. Anyone have any questions so far? Okay, so now I have 3 equations. I have my equation to lowest order, right? So what's my equation to lowest order? It's just H0 sine 0 equals En0 sine 0. That's my lowest order equation, right? My first order equation, so to order lambda, my first order equation is H1 sine 0 plus, H0 sine 1 equals En1 sine 0 plus En0 sine 1. It's my first order equation. Okay. And my second order equation to order lambda squared, so to order lambda squared, second order equation is what? Can someone tell me the second order equation?
Just H2 bar, like H2. Okay.
Yeah, go ahead.
I even don't know how to like spell it.
I'm just pulling out the, See, the reason I organized it with powers of lambda is now I can write them out as 3 separate equations. So you see, I've taken the terms that I've gotten with lambda that are first order terms, right? And I can write that as an equation to first order, right? Now, all I have to do, I have my second order terms written out. That's why I grouped them together, right? Just algebraically. So now I have an equation for second order, right? It's just these terms equaling these terms. So my second order terms equaling my second order terms. Does that make sense?
Yeah.
Okay. So my second order equation is just going to be H0 psi n2 plus H1 psi n1, right? Equals En2 psi n0 plus psi n2 En0 plus psi n1 En1. Okay? So now we have basically perturbed expressions. And it's really funny because I'm writing a cosmology paper right now, and the perturbations in general relativity are so complicated. So quantum mechanics is actually not so bad. You just kind of expand it. Now, obviously, psi n1 and h1 could be very complicated things, as we know. Okay, this is sort of misleading because I haven't told you any energy, I haven't told you any Hamiltonian, I haven't given you any wave function, right? So these are going to be very kind of tricky expressions. And of course, we know wave functions are integrals, right? So, I mean, everything here we're going to have to kind of work with. Any questions on anything here? Okay. Okay. Can I erase? Are we good? Oh man, Austin, I'm sorry. Look at you. Austin comes in and the board is filled. Okay, any questions so far? Are we good? Okay, so now if I told you to redo this all on your own, you'd be able to. Okay, I'm just kidding, not yet. Okay, I'm going to rewrite our perturbed expressions now for the ground state to first order in lambda and to second order in lambda. Another thing I'm going to do is drop my lambda. I said lambda was some random number, right? The only reason I even brought up lambda when I wrote out the perturbation series was just to keep track of the higher order terms, the first order terms, and the ground state terms. So now let's set lambda equal to 1 and get rid of it. Okay, it was just there so I knew which terms were second order in lambda, first order in lambda, and to 0th order in lambda in my perturbation series. So now I'm going to drop out lambda terms, okay? So here's my ground state, or lowest order Schrodinger equation. Here's my Schrodinger equation to first order in lambda. Actually, I got rid of lambda, basically, already. I just did that by instinct, I guess. Okay, and my Schrodinger equation to second order in the perturbation series. Okay, great. Let's move on. So let's work with the first order equation, and let's do some magic to it. First thing I want to do is I'm going to take the inner product of my first order equation with psi n0. Okay, so let's see what happens. So if I take the inner product of this thing with psi n0, I get this expression. I get psi n0. We all know how to take inner products. Many of you did this kind of thing in your research papers. I take the inner product here. I can pull out the energy. because this is an eigenvalue, right? Eigenvalues I can pull out, eigenstates stay in, psi is an eigenstate. I have sine 0, sine 0. Same game here. En 0, sine 0, sine 1. Okay? So all I've done here is I've taken the inner product with sine 0. This takes me back to lecture 1. What's going to happen to this term? Can someone tell me what this term is equal to?
1.
Yeah, so the Braun-Ketz are equal. Who said that?
Me, answer.
Okay, so what am I left with here, Monster?
You're left with En1.
Good. So this term just goes to 1, so I'm left with En1. What is this term going to go to?
En0. No.
No.
0.
0. Good. So this term drops. This term is going to go to what?
0.
0. Good. And then this term just stays intact, right?
Mm-hmm.
Okay. So I get the following expression. I get that sine 0, H1, sine 0 equals En1. Now, what does this even mean? Let's discuss this. This is a big result. And to tell you how big of a result it is, I literally wrote it in big stars next to the expression, because this is a big result from perturbation theory. And I'll tell you how you should interpret this. I thought long and hard about the sentence I wanted to use, okay? This tells me, and this is going to be confusing. You need to think about this now. The first order correction to the energy is the expectation value of the perturbation in the unperturbed state. Okay, what do I mean by all that? So what am I getting? I'm getting a first order correction to the energy, okay? So this is a correction to my original energy. This is fine, right? This just comes from this expression up here and sort of the ways in which we expanded the energies, right? And I notice that what I end up with is the expectation value of my wave function in the unperturbed state, in the original state, right? So basically, this is really awesome, right? Because I don't really even have to consider how the wave function is evolving. All I need to know are the unperturbed wave functions, which we already know. We've seen all kinds of unperturbed wave functions. And I need to know how the Hamiltonian changes, how the potential changes, and that will give me all corrections to the energy, okay? If I solve this thing out. And remember, this is something you can write out. You can have a Hamiltonian, you can write it in there. These become integrals, right? Wave functions are equal to integrals. Like, you can compute this object. This is something you can compute. And this is why we spent so much time on bracket notation, because this shouldn't just look like random symbols. This should look like something you can actually compute, and you can kind of put the pieces together. So this is my big result from first order perturbation theory. Any questions about that? And you're going to have to sit with it a little bit, and we're going to work with it today. But are there any questions before we get into the deets? Okay, fine. Okay, let me see if I want to do this part. And that's not so important. The first order correction to the wave function. Okay, I guess I can show you this as well. I mean, I wrote this down. It's kind of important, but this is more important. So I'll write it down. Just like I got first order corrections to the energy, which is what we just derived, I can also get first order corrections to the wave functions themselves. Now, the reason I say it's not so important is because what are we usually interested in? We're usually interested in energies, right? I mean, that's the whole ball game of quantum mechanics, and obviously other dynamical quantities like differential cross sections or angular momentums or all the other things we've been working with. But you can also figure out the corrections to the wave function, which makes sense because we wrote out the wave function as a perturbation series expansion in the same way we wrote out the energies. So just using what we wrote before, I get this expression. I mean, this is not so important, but I guess I'll write it down. If you just work out the algebra with all the other bits, I can go over it tomorrow for those of you that want to see how this works. Where my state, psi n1, is just equal to this thing, right? Some multiplicative constant, like we've seen, times the ground state, right? That can take me to one state to the other. And so if I plug this thing back into there, I just get this. My summations are really off. I mean, this is all right. This isn't such a big deal. I'll explain this in a second. Okay, fine. So what am I doing here? So I've written out my first state wave function just as I mean, it's equal to my original wave function times some coefficient. This is all fine, right? And if you play around with the original expression, you can get this equation that can take you from first order states to ground states, okay? I mean, this is okay. It's not such a big deal. If I take the inner product of this thing with psi 0L, see, this is why I made these very interesting choices. So take the inner product with psi 0L. Let's see if I did this right. Oh yeah, this is fine. Yeah. So you just get this. Can I pull that out? Yeah. Okay. And now I have an expression for my completed wave function, right? Taking me from one energy to the other. And I can just plug this into my equation up top. Let me just make sure this is okay. Sometimes I make mistakes in my notes, so I just want to make sure. Yeah, no, I did it right. Can pull out the energy. Okay, and I can get this kind of expression. It's kind of the same thing as what we just pulled out. The only difference is I'm using the first order corrections to the wave function instead of the energies. That's all. Okay. I wouldn't worry too much about that. I just thought I'd show you if you come across an expression like this. It's not so important. The first expression is way more important. Any questions before we start solving problems? I see some new people here today too, so that don't usually get a chance to sit in, so welcome. Like Serafina, Tony. So are we ready to solve problems? Get your pencils ready because everyone's going to be figuring things out with me today. That's what we're going to be doing. Okay, let's start. So let's look at some common potentials we've talked about, and let's try and solve perturbed versions of them. Okay, let's see what we can do with these expressions. You know, the best classes I ever took were flipped classrooms. So I'm trying it today. So I'm not, so the part I want you to read about, so I'll tell you what I want you to read about, is something called Degenerate Perturbation Theory. I don't like the name, sorry. I didn't come up with it. Degenerate Perturbation Theory. So that's what I would have covered today instead of doing problems. And these problems I made up. I would have given you these problems on a homework, but instead you have similar ones on the next homework. But this is what you should read about. This is an important technicality. Okay, let's do a perturbed harmonic oscillator. How does that sound? Lizzie, who wrote her paper on the harmonic oscillator, basically did write a perturbed harmonic oscillator. That's what a dampening force or a driving force is. Okay, so we have H naught. We have our sort of unperturbed potential. What is this? It's 1/2 kx squared. We'll use this version. Okay, we won't use the m omega squared because this is just easier. Everyone knows what this is, right? No one's confused. We feel okay. Okay, again, omega equals root k over m. Okay, and we have our energies. Right, those are my quantum mechanical energies that we've seen many times. Anyone have questions about this? No? So what is an example of a perturbation here? Can someone tell me an example of a perturbation? Like what could they see as being a perturbation to this system? Could be anything, could be any damn thing. I mean, I have a specific one I want to work out, but it could be anything. Rika, what do you think could be an example of a perturbation here? Okay, maybe she's not there. Jenna, what do you think could be an example of a perturbation?
So I'm just thinking of like the harmonic oscillator as just like the spring on the wall, right? That's what it is.
Exactly.
I guess like if I don't know, it's just like
what could I do to the spring to make it move differently?
I guess we'll just like once you like you pull it and release it, right? And then if you just like hit it if you just like touch it again while it's
there you go.
doing its thing.
Yeah, that's an example, right? I pull it, I let it go, and then I hit it again. That's a perturbation. You're stopping its normal potential from working itself out. Good. Perturbation is kind of awesome, right? You can do anything you want and calculate how it's going to affect your system. It's really the name of the game in physics, right? What objects in physics stay constant? Nothing. It's all about what force is acting from what and what's going on as a result of that force. That's all physics is, really, if you want to break it down. So yes, that's a good example. So I'm going to come up with my own perturbation. I'm going to change the spring constant. That's my perturbation. And what I'm going to say is I'm going to slightly change k. Okay, and I'm going to perturb k by some 1 plus epsilon times k. That's my perturbation. And this increases the spring constant, right? So it makes the spring more rigid. It makes the spring less jiggly. So I've made it more rigid. So what could this be? This could be something like I'm cooling my spring, right? I'm making it colder. That's my perturbation. So I've changed the spring constant. Okay, so what happens to my exact energies? Let's think about this. So now V prime equals what? V prime changes, it equals 1/2 1 plus epsilon kx squared, right? Now I have my perturbation in my potential. And my energy now goes to En equals n plus 1/2 En prime now, the perturbed energy, h bar omega prime, which equals what? It equals n plus 1/2, right? H bar root 1 plus epsilon k over what m, right? Now my energies are changed too. Does this make sense? Yes? So now everything needs to be perturbed accordingly. Nothing complicated. Now I'm going to expand my energies in a power series in epsilon. And I am actually going to really show you how to do a power series really slow today, so no one gets confused. Okay, I even wrote it down here. Show them how to do the power series. Okay, so let's do it. So my energy, En, is going to equal n plus 1/2 h bar root k over m. And I'm going to write out my epsilon, 1 plus epsilon as a power series. Well, square root of 1 plus epsilon, right? As a power series, an epsilon. Okay, so f of epsilon equals the square root 1 plus epsilon, right? Because this is the term I took out of here. Does that make sense? Please stop me if it doesn't, because the reason I'm going slow is I want to make sure you're understanding what I'm doing. Okay. So how do I write a power series? In general, a power series equals this. It's the function evaluated at 0. Austin's probably being taken back to Calc 2.
Yep.
Okay, good. I thought I made a mistake, but okay. Already. I'm like, oh no. Plus epsilon df dt evaluated at 0. So it's the first derivative. Plus 1/2 epsilon squared d2f dt squared evaluated at 0 plus dot 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 dot. We drop it off there. We converge the series there. Okay, and for us, square root of 1 plus epsilon, that's just equal to 1 plus, right? Because f of 0, this thing is 0. Square root of 1 is 1, so I get this thing back, right? Plus epsilon 1/2 1 over the square root of 1 plus epsilon, right? I've taken the derivative, I pulled out the half, I have my factor of epsilon out in front, right? So this is just doing that derivative fast, valued at 0, plus 1/2 epsilon squared minus 1/2 times 1/2. These derivatives get really annoying because they're second derivatives, to the 3/2 plus dot dot dot. Please work these terms out when you do this. It's not that hard. And this is just doing the derivative twice. That's why I have 2 factors of 1/2 and 2 factors of epsilon. This 1/2 comes because this was in the denominator as a square. Sorry, this was in a square root. Okay, and doing the algebra, which I won't pain you with, I get 1 plus 1/2 epsilon minus 1/8 epsilon squared. So that's my power series, okay? And now I can plug that in up here. So now my energies become En equals n plus 1/2 h bar root k over m, right? Times 1 plus 1/2 epsilon minus 1/8 epsilon squared. Okay? Any questions how I did all of this? Memories. These are memories because when you actually do this in real life, quote unquote, when you're writing a paper, you never write all this out. You just know what it's supposed to look like. After a certain point, you just know what it's supposed to look like, and you're done with it. One does not spend a lot of time computing things. Well, thinking about this stuff. Any questions? I see some people writing. I'll give another minute. Everyone's okay? Okay. Now the question is, what will be the first order corrections to the energy? Okay, that's our big question in perturbation theory. Okay, so this was our big derivation. We derived a new expression for the energy for the harmonic oscillator. Now notice, guys, that energy that I wrote down, n plus 1/2 h bar omega, remember how long it took us to derive that a few classes ago? We had to use raising and lowering operators. We had to use commutators of those raising and lowering operators. We had to do all that algebra to get n plus 1/2 h bar omega, right? So for those of you that are following or jumping in now, you have to go back and watch that lecture on the harmonic oscillator. Otherwise, you're not going to know where I got that E sub n from, right? Okay. Okay, so what's the first order correction or perturbation to the energy? So I have my expression, En1 equals psi n0, H1 psi n0. Okay, I have that H1 equals H minus H naught. And I have that my original unperturbed potential is 1/2 kx squared. Pretty straightforward. We know our Hamiltonian, right? Our perturbed Hamiltonian is just this thing. This is my perturbed piece, right? Coming from epsilons. This is my unperturbed piece, right? The difference gives me my full Hamiltonian. And this is just equal to 1/2. I did all the algebra for you, epsilon, okay? Which equals epsilon V times the potential. Okay, and we can just plug this thing right in. My first order correction is equal to this thing. I'm going to use some weird notation here, which most people use. So I pulled out my epsilon. Again, that's a tiny number. I can ignore it. That's the whole point of perturbation theory. You're getting approximations. N, V, N. Again, the state of psi doesn't matter here. That's why I wrote a big N. Could be anything because it's just going to be 1. It's not going to affect your perturbed potential. Right? And any questions about any of this? I mean, I just kind of took this result and massaged it a bit up here. And I used this stuff to get this expression, which you can work out in a few steps. Okay, now I'm going to introduce a really important idea. I don't know if you've ever heard of this, Austin, if you've ever heard of the Virial Theorem in your studies.
I have not, actually.
The Virial Theorem is, well, the quantum mechanical version of the Virial Theorem tells you that the expectation value of your kinetic energy equals the expectation value of your potential, okay? And I need to use this to get my final perturbed energy or first order correction. That means that T plus V equals En, right? I can just add those energies up. You should know this from sorry, not all of you have had Miss Delise. Whoever your high school teachers are, you should know this. Okay, I have an expression for V. Okay. What's my expression for V? It's very, very simple. It just comes from this thing up here. It's just 1/2 En, right? Nothing fancy. En being that h bar omega stuff. Okay, so this just equals, right? This just equals 1/2 h bar omega, right? 1/2 plus n. Okay. And there we go. We have a first order correction to the energy. I mean, that's kind of it. There's really nothing else to do. The last thing we need to do is put back in our epsilon, which I kind of ignored up here. But we'll do it. So my first order correction to the energy is just epsilon over 2 h bar omega. I'll just put it back in, 1/2 plus n. This should be a very, very silly derivation. Because what did we figure out here? Can someone tell me what we just figured out? So what was the original energy? The original energy, the ground state energy, was 1/2 n plus, shoot, what was it? H bar omega. Oh no, that doesn't look right. Oh no, you're right. This should be out here. And not that it matters. Okay? So can someone tell me what the first order correction did? What did my perturbation do at the end of the day? What factor did it tack on? Because this is the whole name of the game, right? We want to figure out what our perturbation is going to do to the system. So what did it do to the energy? Did it increase the energy or decrease the energy, and by how much? Did it not do anything? Did it did making the spring constant higher do anything? That's the real question, right? So let's say you have a lab. Jenna has her lab, okay? You're from California, right? I always forget. Okay, Jenna has her lab in California. By the way, the Nobel Prize in Chemistry went to a scientist from 2 Nobel Prizes from California, physics and chemistry this year. I think at Berkeley and UCLA. But okay, Jenna has her lab, and her group studies harmonic oscillators. I don't know where they got the money to do this, but somehow they convinced some people. So she studies harmonic oscillators, and she wants to know, she submits a proposal, what will happen to the energies of my oscillator if I cool the oscillator by this amount? Okay. Now, obviously, if I wanted to cool it by a different amount, I'd have to change my perturbation to the potential, right? Here, I just added some random 1 plus epsilon. It wasn't very specific. Now, the theorist would come to you and say, Jenna, don't worry, this is our prediction. This is what's going to happen to your energy. And if the energy increases by this much, well, then your oscillator is going to oscillate more, okay, by this much, and so on and so forth. So what did raising the spring constant do here in this situation?
If the epsilon is like really, really very small, is it right?
Sorry, say it again.
So is epsilon really, really small number, right?
Mm-hmm. Mm-hmm.
So then it just it decreased, but it's not kind of logical.
Exactly. It decreased the energy, right? Because we're taking En minus En1, right, from our original formula, right? It decreased the energy, but it really made no difference because it decreased the energy by a factor epsilon over 2. Okay? Is that okay? Now, if I wanted to decrease the spring constant, I would have added this kind of perturbation to my potential. Right? This decreases the spring constant, right? Now, let's say I really wanted to decrease the spring constant by a lot. Then I could do something like this. Oh my gosh, that would totally, I think your oscillator would break because there's no such thing as a perfect spring, right? A perfect spring is something that oscillates forever. There's no such thing. Hooke's law fails at some point. So that would break it actually. So here you go. This is a good example of something to play around with. And actually, a lot of times in research, you're actually just playing around with random potentials and seeing what kind of universe you get, in my case. This is the question you ask yourself. what kind of universe would I get if I made the potential do this? And most of the time, as Austin knows from our discussions, the universe collapses on itself.
Yeah, I know you said that's like your finding a lot.
That's my finding. I'm very good at creating universes that collapse in on themselves. So if you want to know how to do that, come talk to me after. Okay, so this is the harmonic oscillator. Okay, so good job. That was a good call, Olha. And we are going to take a 5-minute break, and then we will do the infinite square well with the perturbation. And you guys are going to bring out your integration chops and teach me how to do these. Okay. So we'll be back at 10:30. It's crazy how it's almost November. Isn't that just insane?
Yeah, I can't believe that.
It's just,
We're already almost at Halloween and then it's
I know.
almost Thanksgiving.
I know. It's like, this class has been going at rapid fire pace. Rapid fire pace. You guys have no idea, which is a good thing and a bad thing. It's a good thing because we'll be able to do field theory soon. It's a bad thing because we'll be able to do field theory soon. Which is my bread and butter. Oh yeah, Austin, remember that paper I was working on about Majorana neutrinos?
Yeah, I think I do remember.
So I emailed a few professors about it, and I sent them some of my calculations, and they said that if you to be able to actually figure out this interaction and to get this number out that you computed, you would have to get to an energy at like 40 or 50 TeV, which is like 100 times higher than anything we have right now.
That's really high, if yeah, from what.
It's a flop. It was a flop, so I'm not gonna continue.
Okay.
With that.
I mean, I guess now you know, but
Yeah, you would need. They said you would need a supersymmetric particle. You would need supersymmetry to be real for it to actually work out nicely, which I don't believe in, so I'm not going to keep working on it. What time is it? 28, okay. Are you going to any weather conferences this year?
I mean, everything that would normally happen is virtual. So
Yeah, same
yes,
for me.
probably virtually, which will be
It
a
kind
different
of-
experience. But
Yeah, it kind of stinks that all our conferences are virtual.
yeah, it's sad. But
Yeah. Usually it's so much fun having people come and we're going and
yeah,
being with like-minded people.
yeah, it's fun. I mean, you'll still get to see like research and different things that's going on in the field, so that's still nice. But
Yeah.
it just takes away
It's
that
different for you.
interactive aspect of it, I guess.
It's so different for you guys and for almost every other field because you guys don't have archive. So it's almost like you're not updated like every day like we are.
True. I mean, there are some papers that in my major on archive. I've seen them.
Really?
Yeah, there
Man,
are
they've
few,
really been
but they're
expanding
there.
it. Wow. They've really been expanding archive. It used to be literally just high energy theory for a long time. Like there
I
was
know there is some pure math, I think, on archive now.
Oh god,
too.
I know. There was a lot
I
of
remember we were
outrage.
looking with Johnson like 3 weeks ago or something.
There was a lot of outrage when that happened. Okay. Let's get started. Actually, I'll wait another minute because half our class is gone. Oh my gosh, I feel so bad for Jenna. It's so early out there. I really, but it's tough. It's tough finding the right time, you know? It's really hard because most people are in the East Coast, so.
So are you 6 hours earlier from where we are?
3.
Or 3 hours
3,
earlier.
yeah.
Oh my gosh.
That would be actually insane.
It would
No
be
way.
4 in the morning. Okay, folks. By the way, Lizzie, I got all your stuff.
Thank you.
Okay, so let's look at this. Let's say I threw 2 bosons. What are bosons? They're just particles. We'll investigate bosons a lot in the spring. But let's say I throw 2 bosons, 2 particles into my infinite square well. Now I have 2 things jiggling around between the walls, and they interact with this potential, right? When they hit each other, you get something out. That's it. That's why I have a delta function there, right? When they're both at the same position in time, this thing equals 1, right? And you get some potential. You get some interaction, okay? Just like we saw with our Green's functions that describe interactions. So first, let's ignore interactions and let's write down the first excited state and the ground state energies, okay? And wave functions. So we know from what we derived last time that our first excited state, our ground state wave function is just this. I can go by any multiple of psi, right? So this is something we've looked at many times for the infinite square well. And if n equals 1, psi and, oh god, I want to write this as 1, and x1 and x2. I just have to keep track of my notation. We'll write it at this as 2 separate wave functions for psi, for x1 and x2, right? And so this gives me that psi1, x1, x2 equals 2 over a sine pi x1 over a sine pi x2 over a. Make sense? I have 2 wave functions for each boson in my well. They're in the ground state. N equals 1. We'll call n equals 1 the ground state for now, so it's easy. So I don't have to write x0 and y0, okay? Anything confusing here? We've derived this before, right? We spent a whole class getting this little thing. You know, I read a really beautiful line in this poem by this guy named Arthur C. Great poet. And I was reminded about our class because one of the lines goes, "You may wonder why a meson beam oscillates." So this guy is a poet who went to MIT and he studied physics, and he left MIT 2 years in to pursue poetry. Wow.
Wow.
So
That's
yeah,
interesting.
it's pretty incredible. And he won a National Book Award. Amazing. I mean, he's amazing. And he moved to California, went to Berkeley, and became a poet. Okay, great. But he has this line, so he uses a lot of physics references. So there's this line that goes, "You may wonder why a meson beam oscillates." So meson is a particle. You know, we as particle people, we look at mesons all the time and meson beams. And yes, we do wonder why they oscillate. Okay, so here we go. We have mathematical descriptions of oscillating waves or beams. Okay, looks good. I have two of them. Square root goes away. Fine. Okay. And I can also write my energies, right? We've derived energies. So En equals n squared, pi squared, h bar squared over 2 ma squared. These are my energies. Right, E1 just gets rid of the n because now I know which energy I'm working with. And in our case, we have two particles. So En equals 2 E1, right, equals pi squared h bar squared over ma squared. I just get rid of the 1/2, right? Because we have two particles. So we have two energies. That's all. Okay, for the first excited state, n equals 2, we'll call it. So first excited state, I just didn't want to use zeros to confuse you with all of this stuff too. Okay, n equals 2, we are going to get another wave function, right? We're going to have our wave function from the ground state and the wave function from our first excited state superimposed on one another, right? That's what our formula tells us. So psi 2, I'm gonna write this up top because it's kind of a long expression. Can I erase the potential? Do we know what the potential is? We have it written down. Okay. So let's write down the first excited state. So psi 2 of x1 and x2, 1 over root 2, psi 1 of x1, psi 2 of x2, plus psi 1 of x2, psi 2 of x1. They're going to be written as some superposition of states. Now it's easy, and this is a normalization. Don't worry about it. When we work out the integrals, you'll see why I have this here. I have my 2 over a. I have my sine pi x1 over a. This is just going to have a 2 pi, right? Because it's another multiple. It's the second excitation. Does everyone get how I got this and this? Yes? I'm going up in energy by a multiple of pi, right? So now I go from pi to 2 pi. Does that make sense? I hope it does. Okay. And then similarly here, we just have sine pi x2 over a, sine 2 pi x1 over a. Good? Olha, you don't look so convinced.
About what?
Are you convinced? Maybe you are. I don't know.
More or less.
Okay, fine. That's good enough for now. Tony, are you convinced? I can't tell. Okay, I'll take that as a I'll take that as a maybe as well.
Okay, now I'm convinced. I just wrote it to the end.
Okay, good, good. So you always have to look at it for a second. That's why I said more or less is good enough right when I write it down. Okay, let's do some algebra, which is your favorite word, right, guys? Oh gosh, I hope I did this right. I think I did. Please correct my algebra. I do this. Oh God. That's all I did there? Okay. Man, I really went slow. Wow, that was bad. I just, made 1 over root 2 2 times a into that. Nothing crazy. I don't know why I rewrote everything. I do this late at night. It's like meditative for me, and I'm like, let me write my notes. It's like 2 in the morning, and I'm like trying to work this out. So I guess when I said I'm going slow, I really meant it, because like this is silly, but okay, whatever. So again, E2 is just going to go up another multiple. I put a 2 there. It's fine. Of pi. These should be squares. What is going on here? You see, that's how you know I was asleep. Putting the 2's in the bottom. What nonsense. Okay, this is my second excited energy. Nothing really crazy here. And actually, we're not doing any perturbation theory yet. I hope you guys realize that. I'm not doing any perturbation theory yet. I've done nothing. I know E1. And now I have my first excited state energy eigenvalue. I just add them up. And I get 5 over 2. Okay, I call this E star. Okay, no perturbation theory. I just took multiples of the energies, and I get this out. Has nothing to do with the wave functions, because we derived all of this before. Right? I'm not going to re-derive everything that we've derived. Okay, really, really trivial. And when I say trivial, I know it's probably not trivial to you. I've been there when a professor or a teacher or a friend even says, oh, this is trivial. And in your head, you're going, oh, no, it's not. It's okay. It will become trivial soon. Don't worry. Okay, no perturbation theory. We didn't allow Austin in his lab with a slab coat to do anything crazy yet. We said, calm down. Let's first calculate. Let's first calculate the ground state and first excited state without perturbations in a perfect world. You should also think to yourself, guys, in the real world, how am I going to get from a ground state to a first excited state without a perturbation? How do I even do that? That's not possible, right? It's like the process of going from the ground state to the first excited state is a very complicated process. It's not just like you magically jump from one multiple to another. So when I showed you that, you should have been a little bit confused, although it's pretty close actually, which is pretty remarkable that it's pretty close to just being one multiple to the other. It's pretty damn close. Okay, so let's use first order perturbation theory. And let's estimate the effects of my interaction from the delta function potential on the energies, okay? Now let's take into account the interactions. So remember, I'm not taking into account any interactions here, right? My perturbation is the interaction when the bosons hit each other, when x1 equals x2 in the delta function. Does that make sense? So now let's talk about the interactions. That's where we're going to need perturbation theory. Any questions so far about the conceptual nature of this? I hope conceptually it's clear. I hope conceptually you're not sort of like confused. Okay. Okay, let's bring out my favorite equation now for first order perturbation theory. Okay, which is really the most important thing we derived. We have our potential. By the way, I made up a potential for you guys for this problem, and when I solved it, I got it totally wrong, so I had to redo it. So this is right, believe me. Okay, we have our wave functions. Oh, yeah. Okay, remember, this is just my two-particle wave function. This should be a 1. Sorry, I missed the 1. So let's compute this. Psi 1, 0, H1, psi 1, 0. Right? Now we can actually compute that thing. Like this is something we can compute. It's not just notation. Right? What is H1? It's this part. Right? That's H1. That's my interaction. Yes? Does that make sense? H1 is just this from the Hamiltonian. It's the interaction. It's the potential. The potential is the interaction. The kinetic term in the Hamiltonian has nothing to do with the interaction. Notice how I haven't even brought up a kinetic term this whole time. Right? We've split the Hamiltonian into an interaction piece, our potential, and a free piece, our kinetic. Right? So now I only am concerned with the interaction in perturbation theory. Does that make sense? I hope that makes sense. That should be crystal clear. Okay, so now I'm going to compute this thing because I have all of this stuff now. This is H1. This is my two-particle wave function, right, in the ground state. And now let's compute the perturbation. So now I have 2 over a squared, right, because now I have 2 of these things, right? I'm going to have 2 integrals from 0 to a. Right? Because my wave functions are integral values. I'll have a sine pi x1 over a, sine pi x2 over a, minus a v naught for my potential. I split up my potential just to keep it easier. Delta x1 minus x2. And then I need my other 2 bits. Yep. And I'm integrating over 2 particles, dx1 and dx2. Make sense? Remember 0 to a is the boundary of my box. right? It's where I'm stopping my box. So if I have the box, I'm stopping it at some value a. Okay, that's why I'm integrating from 0 to a. Any questions about this? So this is what this little object is equal to, right? So now we're actually doing the full calculation. Usually if I was just lecturing, I would not even bother with any of this, right? I would just write this expression and then move on to the next thing. So that's why I'm trying this. So you guys let me know if this is more helpful than just jumping to the next topic, which you can read about. Okay, so let's compute this. Let's do these integrals and let's see what we get as their first order correction in perturbation theory. And this is really awesome actually, right? This is actually kind of cool because we're working with ground state wave functions, as I said earlier, right? We don't have to really guess about what's going to happen to the wave function as long as we know what our interaction is going to do, right? Or our perturbation. This particular perturbation is an interaction, but in the harmonic oscillator, my perturbation was different, right? It was like changing the spring constant. That's not an interaction. Any questions? So this is kind of remarkable. I have my interaction, I know my ground state stuff, and now I can compute the first order correction. Okay, let's as Olha asked me a few weeks ago, do the integral. I will do the integral. I will not leave you. I will not. A few nights ago, I was like, I will not leave them hanging. I will do this integral. So I did plow through. So let's do it. Okay. Okay, this is kind of annoying, but okay, we'll figure it out. You get -4 v naught over a. So first I'm going to do the integral over dx2. Yeah, and you will get sine squared pi x1 over a squared dx1. So this is what you get after you do the integral over dx2, which should be straightforward if you know your integration. If you don't, it's okay. Ask Gabe. Now I'm going to use my trig identities, which you all know and love. Okay, I'm going to rewrite this with some trig identities, and I'll get -4. By the way, folks, you should always have like a little sheet of paper with all the trig identities. You use them so many times. They're so useful. They're so handy that, and you like exponential identities, logarithmic identities, the rules. These are just things that it's like when you are learning Japanese, or if you're learning another language, you need to know how all the grammar works. That's what I call the rules. The rules and identities are like the grammar. So I'm just going to use one of my identities from my handy tools. And I get that this is equal to 1/2 minus 1/2 cosine 2 pi x1 over a squared dx1, which you guys should actually recognize. This is kind of a common identity. Still only working with the integral from dx2. Okay, now I'm going to work with this a little bit more. And I get 1/4 minus 1/2 cosine 2 pi x1 over a plus 1/4 cosine squared dx1. This is just doing some more manipulation, multiplying some things out, that sort of thing. Okay, now I use these two identities. Cosine 2x equals 2 cosine squared x minus 1. And that cosine squared x equals 1/2 plus 1 over 2 cosine 2x. Wow, these are fancy identities. Thank God for my identity notebook, which comes in handy so much. Okay, I can erase this, right? We're okay? Yeah? Okay. We're almost there, guys. We are almost there. So now I'm going to rewrite my expression, right? So psi 1, 0, h1, psi 1, 0 equals -4 v naught over a, integral 0 to a, using these identities, 1/4 minus 1/2 cosine 2 pi x1 over a plus 1/8 plus 1/8 cosine 4 pi x1 over a dx1. Okay? Sorry, I'm not doing every little step. It would take too long. We don't have much time. So just work out the steps. The algebra, it's very trivial. And I'll keep going with my algebra. Still just massaging my integral over dx1 minus 1/2 cosine 2 pi x1 over a. Yep, plus 1/8 cosine dx1. This equals doing more. Now I'm going to do the integral over x1. I've exhausted my manipulation. 3/8 a minus 1/2 a over 2 pi sine pi x1 over a 0 a plus 1/8 a over 4 pi. Whew. Okay. This is why I don't do these here, because they're very, very long. There's a lot of manipulation. So I did all my integrals. Wow, this cleans up beautifully. I'm tearing up, guys, because we got the first order correction to the energy. And somehow we get our first order correction. E11 equals minus 3/2 V naught. So I leave it up to you to figure out how we get there. It's not hard. You have to do some algebra. V naught being our V naught is, okay, I'll tell you what V naught is. So remember, my potential V was what? What was it, guys? It was minus A V naught delta x minus x2. Was that our potential? Yeah. So V naught is just a constant with units of energy. So it's a value of energy. Could have named my constant anything here. So I get that the first order correction to the energy is minus 3/2 V naught, which is kind of interesting. This has kind of a very interesting physical significance. So let's discuss that. Everyone okay with that? Do you guys prefer if I do more calculations like this and have you read some of the topics on your own? I'll let you guys finish writing before. Let's take a poll. How about that? Give me a thumbs up. There's like a thumbs up button, right? Give me a thumbs up if you prefer doing calculations over more talking, more lecturing. Okay, okay. I think we have some consensus. Okay, good. So we will do more calculations. But I have to trust that you'll read about the stuff you need to know on your own then, because otherwise, what I'll show won't make a lot of sense. So degenerate perturbation theory. I hate that word, right? Degenerate. What a silly word. Not good. But that's what it's called. So, but let's wrap up before Gabe gets in here. Let's discuss what we figured out. Let's break this down because this is kind of important. So what did we just solve for? Who hasn't talked yet? Tony, what did we solve for? He might not be there. I don't think he's there. Bob, what do you think we figured out here, to your understanding?
I'm kind of lost in the math.
It's okay, no problem. No worries. Who hasn't talked? Serafina, what do you think we figured out here?
We just solved the series, the integral. I mean.
Uh-huh. Yes. Our final result is a correction to our original energy, right? Now, can someone tell me what is the cause for this correction to the energy? What is the cause? What is causing this correction to the energy, right? What is causing? Like what made this whole process work itself out to this?
The two bosons colliding?
Exactly, the perturbation. Good. So the perturbation caused this correction, right? And what happens when the two bosons collide? What does it do to the energy? Olha answered this for the harmonic oscillator. So what happens here for the energy? Is it going down or up?
It goes down.
Yeah, exactly. So I'm losing energy in the system because of that interaction, right? By some multiple. In this case, it's 3/2 from our potential, minus a V naught times some delta function, right? For their interaction. So yeah, so the perturbation was the interaction, as Jenna pointed out correctly, when they collide. And the energy is affected by that. It's corrected by that interaction. In the free case where the particles weren't, like I had two particles and they weren't interacting and I said, ignore the interaction. There was no correction to the energy, right? We just got our normal energy. We added them up and we were done. Now remember though, before Gabe takes over, this needs to be added to your original energy, to your unperturbed energy, right? This is a correction. It's not your total energy. It's what needs to be added or taken away or whatever to your original unperturbed energies, right? These are the corrections that come from perturbations, in this case, an interaction. And in the case of the harmonic oscillator, our perturbation was raising the spring constant. Okay, all right, great. So next week, we're gonna do WKB approximations, another approximation scheme, which is very important. And now Gabe is going to take over and give what I know will be a Mozart style exposition on contour integrals and poles and skirting poles and
Mozart style, that's a little bit too much.
Gabe, what are your feelings about perturbation theory?
It's pretty useful. You'll see if you ever go into particle physics or anything, it's how people do things.
Exactly, because we can't really solve anything exactly, right?
Yep, it is how it is.
That's how it is, unfortunately. But nature, at least nature gives us something to work with. She
Yeah,
lets
it's
us be
interesting.
sloppy and assume a lot of stuff.
Yeah, and it's like interesting because as you guys are probably seeing this now, like even the problems that like we are working right now in the class, that like if you think about it, they're quite simple, right? It's just like even in the problem set, like for example, Or like, like even sometimes a harmonic oscillator that's slightly perturbed by another potential, and like you need to develop something completely different because you can't solve it. And if you think about it, that's something kind of simple, like conceptually, but it's very, very difficult to do mathematically.
Exactly. Even the hydrogen atom, folks, is such a simple system, right? If you could explain it to a 6-year-old what a hydrogen atom is. And on the last problem set, you saw the electron, or we the electron, right? Which we're not, because it would be insane. The numbers don't add up. But the math gets complicated, but it's okay. We're working through it. Okay, thanks, guys. I will see you next week or tomorrow morning. Those of you that want to chat about anything, college stuff or physics or the class. And like I said, I'll just make this comment one more time, just because different people are here before Gabe takes over. At the end of the course, a week before papers are due, I would like topics, right? And oral presentations will be happening as well. The last 2 lectures, I think, will have oral. No, last lecture. Depends how many people are turning in papers. We might extend it a week, but we're going to do oral presentations for everyone to hear along with your paper. And after that, I will email those that I think should really take field theory seriously. Anyone can stay in. It's not, obviously, it's for the public. We're going to have people from my hometown also joining in for the field theory class. But I will just let those of you know who I think should really pay attention, who I think will be suitable for research. So that will happen after the class. Okay, Gabe, take over.
All right.
Let's talk about Calci's theorem.
All right, beautiful.
I'll make you the host.
Thank you.
Let me just.
Thank you. Have a good day.
You too. Thanks.